Hello everyone, my name is Benedictus William Wicakerty with student ID 2024-32017 and I'm from class A. In this video, I'm going to explain about machine learning project using a support vector machine. The data that I'm going to explore and analyze today is the student's performance dataset. I'll be breaking down everything from data cleaning, exploratory data analysis to feature engineering, and finally evaluating model's performance. Alright, the first thing, we need to import all the necessary libraries for this project. I'm import pandas to handle the manipulate data and the matplotlib and seaborn to help us create some nice visual cleanup set. And of course, since I'm building a SVM model, I'm also pulling in some core modules from scikit-learn to help with data splitting, scaling, and evaluating our model's performance. Okay, so the next step is load dataset. I'm using pandas read CSV function to load the student's performance CSV file and save it into a data frame called df. To make sure everything was imported correctly without any weird errors, I usually just print out the first 5 rows using the head function, which gives me a quick look at the layout of our columns and data. Okay, so now that we know the file is loaded, I want to get a complete overview of what this dataset actually looks like. By running the info function, I can easily inspect the border characteristic of the data. It gives me a clear breakdown of the total number of rows, column names, memory usage, and most importantly, the data type. So I can easily distinguish between categorical variables and numerical scores. Okay, so the next step is looking closer at the output from the info function. We can see that our dataset is pretty solid. It contains exactly 1000 rows of data and 8 columns. The text columns or categorical data are stored as object types while the student score are stored as integers. And then to officially confirm if we have any blank spots or missing entries, I run a quick check using isnull sum. As you can see from the terminal output, every single column returns a big fat 0. This is perfect news because it means our dataset is completely full and clean, so I don't have to spend extra time doing any data imputation or dropping incomplete rows, and I can move straight to the next steps. Okay, so the next is to wrap up our initial data inspection. I want to look at the descriptive statistic of the dataset. For this, I use the describe function. If you look at the output on the screen, the Python automatically calculates the key statistical metrics, but only for our numerical columns, which are the math, reading, and writing scores. And then to preparing our target variable for the machine learning model, since the goal here is to predict the gender of the students based on their exam scores, we need to convert the categorical gender column into a format that the algorithm can understand. I did this by mapping the text values to binary numbers using the map function, where females are encoded as 0 and males are encoded as 1. Okay, so after transforming the gender variable, the next thing I did was print out the first 5 rows of our updated dataset just to validate that the changes were applied correctly. Looking at the new data frame structure on the screen, you can see a brand new column named Y has popped on the far right side, and it's working exactly as intended. Rows 0, 1, 2, 5, and 6, which say female under the original gender column, now correctly displays a 0 in the Y column. Okay, moving on to the step 9, we need to handle the remaining categorical columns like race, parental education, lunch, and test preparation course. This basically breaks down every text category and into its own separate column with binary values of 1 or 0. After the encoding process was done, I wanted to review the final look of our data frame, so I printed the first 5 rows using the head function again. Looking at the output on the screen, can see that our target variable y and the original test scores are still there in their raw numerical form. Now that our encoded dataset is ready, the next step is to clearly separate our features from our target variable. For the feature which we represent as capital X, I use the drop function to remove both the original gender column and our binary target Y. Making this clear separation is super important because it tells the SVM model exactly what data it should use to learn patterns. We have separated our features and target. We need to split our dataset into two parts, a training set and a testing set. To do this, I use train set, a function from scikit-learn. I set the test size parameter to 0.2, which means exactly 80% of our data will be used to train the model and the remaining 20% will be locked away as a test set. Next up is feature scaling, and this is a highly critical step for algorithm like SVM. But right now our exam scores range from 0 to 100, while our one-hot encoded features are just zeros and ones. If we leave them like that, the SVM model will think the exam scores are way more important just because the numbers are bigger. Okay, and with our data perfectly scaled and ready, we can finally build our machine learning model. For this project, I am initializing the support vector classifier, or SVC. By choosing a linear kernel, we are telling the SVM algorithm to look for the most optimal straight line or hyperline that can cleanly separate the female and male student group based on the features we provided. Now that the SVM model is fully initialized with our linear kernel, it's time for the most exciting part, the actual training process. To do this, we use the fit function, passing in our scaled training features alongside their corresponding true labels. During this phase, the algorithm goes through the data analysis, the relationships between the student scores and backgrounds. With our model fully trained, I can now put it to the test by making predictions on data it has never seen before. To actually see what the model has come up with, I used a simple print statement on our variable. If you look at the terminal screen right there, it displays a long array of zeros and ones, which represent the raw outputs, a prediction made by the model for each test student. Moving on to the step 18, we are going to calculate the overall accuracy score of our SVM model. To do this, I use the accuracy score function, which basically compares every single prediction the model made with the actual true gender labels. Now, a 69% accuracy score is great, but it doesn't give us the full picture of where the model is succeeding or failing. However, it also reveals our exact errors. 25 female students were misclassified as male, and 37 male students were misclassified as female. To make those raw numbers a lot easier to read and interpret in step 20, I created a visual representation of that confusion matrix. I set up a custom plot size using matplotlib. The darker blue squares along the diagonal instantly show us where the model got it right, making our final evaluation much more professional and easier to represent. Alright, step 21 takes our evaluation a bit deeper than just overall accuracy. Seeing this number hover closely together tells me that our linear SVM model is quite stable and doesn't heavily bias or lean toward one specific group, giving us a well-rounded classification performance. Now let's pivot into the exploratory data. I use Seaborn CountPlot function to look at the exact balance of male versus female students in our dataset. Looking at this bar chart, the chart instantly shows us that the two bars are almost identical in height, with female students being just slightly higher. This visual proof confirms that we are dealing with a balanced dataset, which is the perfect scenario for training a machine learning model. Okay, moving on the step 23, I wanted to analyze how the students actually perform in their math exams. To do this, I created a historical using the math score column, dividing the scores into 20 bins for better granularity. This gives us a classic bell-shaped curve, meaning the math scores follows a pretty standard normal distribution. Okay, moving on to the step 24, I'm looking at the correlation heat map of my dataset. Looking at the metrics on the screen, the colors transmission are extremely strong positive correlation between reading scores and writing scores, which sits at a high 0.95. This tells us that students who perform well in reading almost always excel in writing too. For step 25, wanted to see if taking a test preparation course actually makes a difference in a student's performance, specifically focusing on their math scores. I used Seaborn's box plot function, splitting the students into two groups. On the x-axis, those who took none, and those who completed the course. And step 26, we have the visualization of our actual prediction versus the true labels. The blue line represents the actual gender of the students, while the orange line shows the prediction made by our SVM model. Wherever the lines overlap perfectly, it means the model guessed right. Where they separate, that's where the misclassifications happened. Seeing them side by side like this gives me a fantastic direct visual of our model's 69% accuracy in real time, showing that it successfully captured the general rhythm and pattern of the true data. And that brings us to the end of the project. I successfully went from raw data to a fully working SVM model, and I uncovered some really interesting insights about student performance along the way. I hope this walkthrough was clear and helpful for you. Thank you so much for watching. Don't forget to like and subscribe. I'll see you in the next video. Bye.